Welcome to the session. Greeting of the day. In today's class, we are going to talk about liquid penetrant inspection methods. In this liquid penetrant inspection methods, you can able to see we have taken the penetrant and poured the penetrant over there. After that, we have given some dwell time with respect to the dwell time. Then we have applied the developer, and after application of developer, again we have given some dwell time for the penetrant should absorb dragged by the developer, and then it is giving some contrast color, and we are doing the inspection. But we want to know about this penetrant a little bit more informations. Its property, how it is going inside, capillary action, capillary force needed to go inside the crack. We have a sample in such a way, and there is a small crack over here. When we are doing, penetrant is filled over the surfaces, it fills down here inside, and then when we are applying the developer over there, it comes out, and then this penetrant will be looked at differently, therefore we are able to find it. So we want to know something about this penetrant. Penetrant having properties. That penetrant property makes the process easier in such a way, wettability going inside and absorbability. So those things we have to see now. Penetrant materials. The penetrants are mixtures of organic solvents which are characterized by this penetrant should have this property. That means ability to wet the material. It should not flow. We should touch, wet and flow. Wet the material, ability to spread rapidly over the material. It should not, like denser, it should not be stopped at one location. It should spread and it should flow over those gaps. Then only it is easier to do the operations. If it is stopping over at one point, we can't able to find the defects in the remaining places. So ability to penetrate into the crack in minutes, less than time it needs to be, quickly it should happen. These materials used today are much more sophisticated than in the previous days. In 1900s they used kerosene, oils and contrast carbon black colors over the white. So such methods they follow. These methods are somewhat very difficult when comparing to this normal dye penetrant inspection methods. There they have used kerosenes and whitening methods, first used in the railroads inspections near to the 20th century. But nowadays in the past in the recent years, now we are using this dye penetrant inspection, which gives the contrast in the red color, and the fluorescent penetrants and dye penetrants we are using for our contrast visuality. It makes the process easier. Today's penetrants are carefully formulated to produce the level of sensitivity desired by the inspector. How much sensitivity is required? A level 1, a level 2, level 3. So such categories are there. For low sensitivity we can use a level 1. But high sensitivity to inspect a precious point where we need 200% perfections. There we are using a high sensitive material to interact with the specimen to identify the minute cracks also. So generally I am writing here, penetrant material should have some characteristics of a liquid penetrants. It should spread easily over the surface being inspected. We have a surface here, and from one end we are pouring, everywhere we are pouring, it should spread equally and it distributed all the zones. It should be distributed very well. So that viscosity to be very low, then automatically it flows easily. It should be easily drawn into the discontinuities by capillary action. It should not be harmful to the inspector or of the materials. No odorless or non-toxic or the property which it should have. If it is toxic, it is dangerous. If it is very odor, some smells are coming, it's also sometimes it will irritate us, irritate our noses and humans. It should remain in the defect but remove easily from the surface of the part. Water washable. So these things all recommended. So it should possess a high indicating capability and with less dwell time. That means due to low viscosity, we are flowing, it is evenly flowing through there, and it should come in contact with the cracks, and within a seconds we want to clean. It means the productivity to increase in the company. Therefore, this dwell time should not take more long to flow inside the cracks. All these things should happen quickly. So those ability should have for the liquid penetrants. It should remain in the fluid state, so it can be drawn back to the surface of the part through the drying and developing steps. Yes. It should not affect the physical and the chemical property of the testing material. What is this testing material? The specimen. What we are going to do inspect, where we are going to do the inspection. Inspection we are doing on any surfaces of the boiler plants. It should not corrode this case. This is a liquid material. It should not make any chemical reaction over there. If it is making, the material may corrode, or maybe dust may form, or impurities. It should not harmful to the specimen where we are doing the inspection. It should be cohesive, adhesive, and relatively at a low cost. We should finally have with all these properties, we should have some low costly, it should be available in the market. Then only it will be easily used by the inspectors. We want to talk about a few things about these properties. Now only we have talked about this capillary force, surface, and these are the various penetrant materials property that should have technically. So we have talked about wettability, high flow rate, low cost, non-toxic ability. So this wettability does not comes in specially in quickly. It has some specific value like a contact angle, how this is falling over the specimen, and then how it is generated. You see, we are having a material like this. We have a sample, right? And let us assume the sample having, this is a solid where we are going to do the inspection on these things. During inspection, we are applying the penetrant. Let us assume we are applying the penetrant here. I am applying the penetrant here. Right? In this penetrant, this is something a liquid. And I am understood this. This is the solid. Now you see, we have there is a contact between this liquid to this solid. Some solid to liquid interaction takes place. It means there is some energy is there which bonds this liquid and solid material. So surface energy, it is available there. There are two chances are there. So I am taking a sample which is a fixed one, and I am taking a liquid also. Right? This is a liquid. Somehow we draw smoothly. So this is the sample, and this is the liquid. So we understand this. So this is the solid. So there is a solid liquid interaction. Solid liquid interaction takes place here. So there are two chances are there. What are the chances? So in the solid liquid interaction, this liquid will wet the surface. Wet the surface, or otherwise, second option is there. Liquid will not wet the surface. Notice that there are two chances are there. This two options of wetting and non-wetting. Wetting are both based or depend upon one property. I am calling this as a contact angle. So I am calling this as a contact angle. Where this is contact angle? We are seeing here, see, this is the contact angle. See, I have a liquid here and I have a surface, solid surface. I have a contact angle here. So this is what the contact angle of theta. I am calling this as a contact angle. Contact angle. So this contact angle to be greater than 90 degree or less than 90 degree. If it is contact angle theta is greater than 90, what happens? But the same contact angle less than 90 degree, what happens? Our case, if it is greater than 90, it is not getting a flow, it is fixing there. It should be less than 90 degree. If it is less than that, it is giving good wettability. If it is greater than 90, not good. Not good wetting. So these are the chances of making the wetting actions. With respect to this, I am further moving here. See, I am coming here back with some influences. So I have a surface, right, and I have a liquid, and I have a contact angle. So this is, I told this is a theta. Right? So here, the one terminology is there called as surface energy or surface tension. So here, this surface energy between, here we have a surface energy of a gamma solid to liquid. So it has a contact here, you see, this is the contact point. Surface energy of solid to liquid. Now I am writing here I am writing a surface energy between the liquid to vapor. This also chance. And one more is there, you see, here, this point. Somewhere, any other where the liquid is not there. There is a surface where we can tell we have a surface energy of solid to vapor. So solid to vapor, or three chances are there. So I have written as gamma SL, surface energy of solid to liquid, otherwise you can tell gamma LV, it means surface energy of liquid to vapor, otherwise we can tell gamma SV, this one, this point. I am calling this as a surface energy of solid to vapor. Now you find we can create one equation based upon this. Surface energy of solid to liquid is equal to, so I am solid to liquid here, this contraction is equal to surface energy of solid to liquid plus surface energy of liquid to vapor, here we are having some differences of angle, contact angle theta. So from here we can able to find the, if we know the surface energy, surface tension, so we can able to find the theta. So therefore from here I can able to move that theta equal to cos theta equal to, I'm converting this equation in such a way. So this is SV, surface energy of solid to vapor, not SL, surface energy of solid to vapor. Surface energy of solid to vapor is equal to surface energy of solid to liquid plus surface energy of liquid to vapor cos theta. From this equation we can able to find the contact angle theta. So theta is equal to surface energy of solid to vapor minus, I'm going this side, surface energy of solid to liquid divided by surface energy of liquid to vapor. So I am converting this equation in such format. From this we can able to find the theta. So in case if this theta, I am taking this theta here, in case this theta is less than 90 degree, what happens? In case the theta is greater than 90 degree, what happens? So you see, we are talking about the wettability part. So the liquid will wet the surface. Here liquid will not wet the surface. So this equation is called as Young's equation. Okay. With this contact angle, we are delivering these 2 points. One is regarding the less than 90, wetting is possible. Or one more is the greater than 90, wetting is not possible, or it is becoming a delaying process. Now we come to the other part of one more called as capillary action. So this is one of the important parameters. So we have talked about this point now. This was the equations we created for this purposes. If the contact angle is very smaller contact angle, if it is small, it means this is less than 90. It is less than 90 degree. What happens? It is good wetting. It's evenly spreading over there. If the contact angle is very large, here like this conditions, it is very large, greater than 90 degree. So what happens? It is stopping there, and it is not spreading towards the surfaces. So this is one of the important things that we have to understand. Now again we come across capillary due to this surface forces energy, surface tension. What happens? Capillary is nothing but it is ability of the liquid to flow into a narrow space without the assistance of external force. We are not giving pressure over there. You see, this is the liquidus pipe and tube. We have a liquid at the bottom, and we are keeping the tube inside. There is something happening to push automatically. We are not giving external force. It pushes the liquid towards the upward direction. That is happened by the capillary action. So nothing but a force. Capillary force is generated there. An external force, a surface energy has between these two. That makes, let us assume we have a material like this, somewhere a crack available at the center, and this is the surface. So you see, this is one surface, and on other side, this is one more surface. So these two have some energy. It means surface energy. Surface energy. This surface energy, when I am pouring this penetrant material at the top, the surface energy attracts those liquid automatically, and therefore this penetrant material fills here. Therefore this penetrant material is filling here. This process happening is called as capillary action, which happen due to some surface energy. Here, if it is surface energy, which creates this attraction process on the narrow surfaces. I am calling this as a capillary force. When we are using a menses and dipping into the liquid, due to the capillary rise, the menses will fill. The liquid is going inside the menses. So it means a pipe I am keeping there. So this is known as the capillary testing process. So you see, before going there, we want to find about a capillary, how it happens. The capillary due to surface tension. So we find we understand this. There is something. So we have taken a sample. I have taken a sample. So there is a small crack is there, and we have a surface tension here. So what is the capillary due to? Due to surface tension. So I want to willing to find this. So capillary due to surface tension. How we can able to find it? So we know this is gamma LV liquid to vapor. Where I'm doing this in the here I have spreaded the liquid. So surface tension of the liquid is there. Here, surface tension is to move to the vapor, and in between the capillary force should act to take this liquid inside. Let us assume this is a equation of depth of 2r. I have taken a so the same diagram I am drawing again here in this way. So I have a pipe. The crack I have converted into pipe format. So we are talking about capillary force. So this capillary force I have taken in such a way that it has to go deeper. You can keep like this. So this height is called as 2r. Now the capillary force is equal to 2 pi r into the surface energy. It means surface tension of liquid to vapor. Liquid to vapor. So this is how we can able to form the equation. Now we can add this contact angle also. Where is this contact angle here? So the liquid we dropped there is here. It has to come down here. It has to come down. So the contact angle. So we have contact angle theta is here. So this end, this is called as contact angle theta, where due to capillary action the liquid comes inside. So this is the height of the depth of the where it is going. We can able to find the depth also if we are solving these equations, on the radius of the crack also it is possible to find. And converting this is a 2 pi r delta LV is equal to, I am converting into, so find this contact angle. So pi r square into density, the height into gravity. So I am calculating all these things. So what happens now? So we can able to convert the height separately. Is h is equal to, so I am cancelling this square r and this r and this pi and this pi. All these things I am cancelling. I am writing. We can write 2 h we need. Okay, 2 into surface energy of liquid to vapor, right? This we have to bring it to downward direction. Here we have left a word of cos theta. Right, and therefore it is cos theta divided by this one, r is there, r rho into h we have, and g. Right, where this This R is the crack radius, and rho is the density of a liquid, and G is the acceleration due to gravity. Due to gravity. So I'm trying to find the height. This height, how it is forming with respect to this contact angle and all. So here the capillary force from this I am finding here. So there is somehow minimal one which is required to create the sucking process and moving out of the press also. So here we want to maintain a cleaning, surface cleaning to be done proper. In case if your surface cleaning is not done proper, this contact angle will not come less than 90. Some obstacles will be there, some impurities will be there, some scales will be there. So some dust particles will be there. So all these things makes droplets not to wet the surface and not to move the surfaces. We need a flow. Even though we are giving a low viscous material towards the flow, the dust particle which is already present on the surfaces makes the liquid to stop. Therefore it is not moving, therefore we are not getting the angle. So let us assume we have a sample here and we have some impurities also here. So I have some impurities here and there. Now I am dropping a liquid inside. So it is falling over there. It is falling over there, and in this place it is falling. I have some impurities here. I have some impurities there, which is obstructing. It's obstructing here. Therefore, what is the angle now here? The angle which is adapted here, it is greater than 90. It is greater than 90. But the same thing, when I am doing clean the process, I have cleaned now. No impurities are there. Now what happens when the liquid material is dropped? It is floating over there. It is easily floating over there. Therefore, what happens? The contact angle. So the contact angle will be less than 90 degree. Okay. So this we have to maintain. It means the surface cleaning is most important. We have studied in the procedure pre-cleaning process, and then application of the penetrant. Even the application of penetrant, pre-cleaning is most important there. If you have not done this pre-cleaning process, contact angle will not come, therefore wettability will not be there, therefore flow of the liquid into the crack areas will not be there. So this stops the process. We won't get the accuracy of results we want to get. It will end in the error. So surface energy involved in the crack surface. The surface energy will drag the liquids. So we have talked already this point. The surface energy we have this point, and this point having some surface energy which is wanted to drag inside, and it is going to fill. So all these things based upon the contact angle and the surface tension of this surface and the liquid, which all together comes with a terminology of capillary force. See, it is the ability of the liquid to flow in the narrow space without the assistance of external force. This property helps the penetrant to fill the void. When we are using the meshes to dipping into the liquid, all this comes out automatically. So this is one of the important parameter what we understand. Both wettability and non-wettability all are depend upon this contact angle, and the capillary force actions also involved on those things. So we have to see some of the properties of the good penetrant. So good penetrant should have a good capillarity, force, surface energies involved there. That is nothing but a surface energy, surface wetting capability. And then the viscosity, one by one we will see viscosity, surface specific gravity, water washable penetrant, thermal stability, volatility, fluorescent dye thermal stability. Here, water washable penetrant thermal stability. There are two types of penetrants are there. One is water washable normal penetrant, and one is fluorescent, which is very contrasted brightly when the rays is passing there, lighting forces, it reflects there. Therefore, it is more brighter and it is more contrast. It is very easy to do visual inspection, to see. That's why fluorescent dye penetrant and water washable dye penetrants are there. So, fluorescent dye penetrant thermal stability and this water washable thermal stability. And about the flash point, always the flash point to be higher. There should not be any accidents. Therefore, it should be higher. We will see. The remaining topics of the subject we will see you in the next session. Thank you.